Hello, good afternoon. We are Miranda, Valeria, and Andrea, and we're going to explain our X-ray phantom for the course of analysis of imaging systems.
At CE3M, we perform a high volume of X-rays where consistent image quality is key for diagnosis and patient care. However, most quality assurance phantoms are costly, bulky, and not adapted to modern systems. Our project proposes a low-cost modular phantom with a standardized acquisition protocol designed to improve quality assurance efficiency. We work with the Philips VV Pulsera C arm, commonly used in surgeries, and its mobility and advanced imaging features make it ideal for both clinical use and quality assessment. Together, these tools enhance our quality assurance process and align with real operation room needs.
Our objectives are twofold. First, to develop a reproducible image acquisition protocol for digital radiography. This protocol is designed to measure three image quality parameters: spatial resolution, contrast, and noise. The second objective is to validate its performance against the international QA parameters. In terms of scope, we focus exclusively on digital radiography modalities and use phantom based measurements. Overall, our work aims to establish a solid and standardized method for evaluating image quality in X ray systems under controlled and repeatable conditions.
At the heart of our solution is a 3D printed phantom composed of four stacked levels, each designed to test specific imaging parameters. Level 1 contains a layer of clear gelatin, serving as the base medium for image acquisition. Level 2 incorporates the fine metallic powder scattered throughout the layer to simulate image noise and scatter effects. Level 3 includes a series of slits with precisely spaced separations ranging from 3.5 millimeters to 13 millimeters, designed to evaluate spatial resolution. Level 4 holds a set of objects with varying densities, including Mexican 5 pesos coins, a nickel coin, staples, paper clips, cardboard, and aluminum foil, to test the system's contrast resolution. This multi-level design enables a comprehensive assessment of image quality, combining noise, resolution, and contrast evaluation in a single scan.
We acquire images using the imaging modality of digital radiography, and for these scans, we use a tube voltage of 48, 50, 54, and 56 kilovolts peak, and a source to image distance of 75 centimeters. We ensured that all Phantoms modules were captured in a single projection. Before each acquisition, we carry out mechanical and radiation safety checks in accordance with international standards.
I'm going to summarize the software tools and metrics used to evaluate our X ray images. First, we measure the spatial resolution in line pairs per millimeter using a custom designed phantom, which help us assess the system's ability to distinguish fine structures. For CNR, contrast to noise radio, we select polygonal rows over the inserts and the gelatin background and apply the formula using the difference in mean values and the standard deviation. To evaluate noise, we calculate the standard deviation in uniform areas and supported the analysis with SNR and coefficient of variation. All calculations were performed using custom MATLAB functions where we manually select each row to ensure accurate results.
Here are some example images. On the right, a digital radiography projection showing the contrast module, and on the left, a single digital radiography that captures all three modules simultaneously, which is the spatial resolution, contrast, and noise module. We perform four replicate scans for each modality to test protocol robustness.
We evaluated the spatial resolution of a Philips BUV Pulsera C-arm using a phantom with 16 line pairs ranging from 2.8 millimeters to 13 millimeters. Measured distances between lines were converted to lines per millimeter and compared with expected values based on the phantom's physical design. The graph shows an inverse relationship. As spacing decreases, resolution increases. The maximum measured resolution was 0.179 lines per millimeter at the smallest spacing, 2.8 millimeters, while the lowest was 0.0375 lines per millimeters at 13 millimeters. These values align well with the phantom design, confirming the system's ability to distinguish structures at different spatial frequencies. Although the C-arm can theoretically reach 1.2 to 2.9 lines per millimeter, depending on the intensifier, so our phantom was not designed to test those limits, but rather to validate whether the system can resolve specific clinical level structures.
In this slide, we're looking at the contrast to noise ratio, or the CNR, for each of our inserts compared to the gelatin background. At the top right, we can recall the formula, where mu is the mean signal and sigma is the background noise level. In our case, the background has a mean of 210.5 gray levels with a noise standard deviation of 3.7. 5 peso coin for the CNR of 32.7 and the nickel coin for the 29.6 produce extremely high CNRs, well above our past threshold of 2.0. So, as expected, metal inserts pop right out of the image. Staples with a CNR of 11.7 also show very strong contrast, making their fine edges easily visible. Cardboard with a CNR of 4 sits comfortably above the detectability threshold. You'll see these inserts clearly, but they are noticeably less bright than metal. Aluminum foil with a CNR of 1.9 is right at the edge of detectability, its CNR just below 2, so foil barely is distinguishable from gelatin under these acquisition settings. The key takeaways are that the metals are trivially visible thanks to their very high CNRs. Mid attenuation objects like the cardboard are still detected reliably but with lower contrast. And the very low attenuation materials such as foil challenge the system and may require adjusting imaging parameters or additional processing. In short, these CNR results not only quantify how well each insert stands out, but also guide us to where the protocol is the strongest and where we need to refine it to capture most subtle contrasts.
To make the noise analysis, we randomly scatter iron filings in the phantom to introduce non-homogeneous noise distribution. And we use two metrics to analyze this. The first one is the signal to noise ratio that measures how strong the useful signal is compared to the background noise in an image. It's expressed in decibels and help us to define the image quality. So a higher SNR have a better image quality. The other metric is the coefficient of variation that quantifies the relative variability of pixel intensity in an image. So a lower coefficient of variation indicates more consistent pixel values and more uniformity in the image.
To wrap up, our project demonstrates that the locus phantom and acquisition protocol are fully capable of evaluating the key image quality parameters: spatial resolution, contrast, and noise. We reached a spatial resolution of around 0.18 lines per millimeter, with metal inserts showing very high CNR values above 30, while even materials like cardboard remained detectable. These results are consistent and aligned with clinical QA standards. However, we also found that very low attenuation materials like aluminum foil challenge the system, which helps us identify where further improvements can be made, whether by adjusting imaging parameters or refining the phantom design. Most importantly, we built a fully functional MATLAB toolkit that allows for customizable and repeatable QA analysis without the need for proprietary software. With this, we are now ready to propose a pilot implementation at the center as part of their training and QA routines.